Hi, I would like to talk about maximum likelihood estimator in this additional lecture. This is not a bonus lecture, it's just a supplementary exercise, I may say, or supplementary lecture, whatever you would like to call it. I would like to first of all solve the assigned questions in a little bit more in a little bit detail related to maximum likelihood estimators, because I believe that's a little bit of a tricky topic, and as I try to point out, it is an important topic, especially for those who would like to continue later in their career with something related with data science, machine learning, whatever you would like to call it. So I would just like to straight dive into these kind of questions. So the first question I assigned was 7.38. For those who don't have the correct textbook or the edition, what it says is X is essentially geometric distributed with parameter P. And it says find the maximum likelihood estimator estimator of P. I'm, by the way, just copying the question. On a random sample of size, on a random sample of size, does it say n? Yeah. This basically means, what it means, first of all, let's try to visualize it in our mind. What it means is this. Let's think of again a process which is obeyed, which is governed by geometric distribution. This may be, we have a factory, right? And this factory which let's say produces an item, right, in a kind of, right, this whole thing is sliding, and we check each of these items and we see that, okay, this seems good, this seems good, this seems good, and we stop the process when we for instance, we examine this product and we see that there is a problem with this product, and at this moment we stop the process, and therefore n is going to be that number here. So you may think about here, 0 is going to be corresponding to what we call failure in terms of geometric process. Not that 0 is going to be a failure, is taken to be equal to 0, but in our process this is going to mean a good product. I guess the idea is, I hope it is clear, because as you have zeros or good product, you just skip, you take the next one. Therefore, from a geometric distribution point of view, this is a failure. And success is, in terms of geometric distribution, success which corresponds to 1 is actually a bad product, because once we understand that there is a bad product, it means we have success because we stop the geometric process. So therefore we have a process like 0 0 0 0 0, and then we have 1. And how many of these? Let's say we have 1 2 3 up to n number of values. So basically what we have here is, let me say, a random sample of size n. It means we have these observations. So, well, a typical example maybe, let's say that we have a sequence like that, 0 0 0 0 0 0, another one, and then 1. Let's say that this is our sequence. So this is not a set or each of different so this is not a set. Well, in a way it is a set, but not to be confused with different samples or different observations. Let me get rid of these curly brackets. Anyway, so starting from the first observation to 1 2 3, we have 8 observation here and the first observation here, and these are the results. Therefore, this whole thing, however you, without curly bracket or with curly bracket, however you denote it, this is going to be our sample. 7 zeros led by 1 here at the end. This is going to be our sample consisting of 8 observations. Note that the last one is going to stop the process. So in this case, let's say that this is the sample that you have. From this sample, you would like to estimate P of this process. This is exactly the typical question that we have. You can, of course, apply to any scenario that you have. But what we would like to obtain here is this p value, this p parameter in geometric distribution. And note that there's a hat here because in real life we would never be knowing this p parameter value. On the other hand, from this sample, we can estimate. Remember the paradigm I'll try to present in chapter 7, lecture 6, which I usually confuse. We have a population, and here this is going to be our population, the factory which produces all these infinite number of products, but it's going to obey a distribution parameter p, which we do not know. And in order to estimate this distribution parameter p, we take a sample, and here this is the sample. From this sample, usually it consists of not a very large number of elements. We try to come up with this p, and maximum likelihood estimator, which we are going to denote with ML, is a specific type of an estimator, which can be used for any distribution. And as long as you know the distribution and you come up with the distributional parameters. So that's in a nutshell what the whole question and what maximum likelihood estimator is. Note that maximum likelihood estimator is not the estimator. It is not the estimator, but a estimator. There are other estimators like Bayesian estimators, like estimators produced by method of moments, or just estimators that you can come up with, and they have all different properties. Among those, maximum likelihood estimators is some of the best properties, I may say, or pretty much good properties. So just to remind you what this is, actually, if as you increase the sample size to infinity, this sampling process, as the sample size is increased more and more, what you obtain as the estimate here becomes a consistent estimator. I couldn't spell it correctly. Let me try again. Consistent estimator. What does that mean? This is going to be unbiased, and the variance is going to go to 0. And this is the perfect estimator that you can come up with. Well, so in real life, you may say, what's that? So can there be anything better than that? The problem is it says n goes to infinity. When n is small, we have problems here. So you cannot guarantee that it's going to be a great estimator, blah, blah, which is all related with what statistics and machine learning is about. But just as this is what we call asymptotic result. So asymptotic properties of maximum likelihood estimator is great. So anyway, now let's go back to the question. From now on, the questions is going to be faster, because once we get through this whole scenario of maximum likelihood estimator. Well, the only thing that you need to know or assume at the beginning is we have to assume the correct distribution for the process. And this is a tricky part. You may easily ask, so how can we, since we do not know the population parameter, how can we know that this population is or obeys a certain distribution? Actually, we cannot. We may know it through some experience or assume it through some experience, but always, whatever you start with statistics, you always do some tests at the end. We are going to cover this hypothesis testing concept in the forthcoming chapters, but there are going to be a couple of things also we are not going to be covering, such as assume a distribution. Then we, in real life, in actual statistics, we check whether this distribution is valid. Here we are not going to go through that step, but we just assume that this is valid for the let's say initial level of this course. Anyway, so what we have is these samples. From these samples, what is the value of p? First of all, intuitive result. What I suggest is actually, up to this point, in many cases, I have always wanted to solve the question rigorously, but I also want you to always keep an eye for the intuitive solutions. Do not present me the intuitive solution, but in order to understand the whole picture, try to combine the rigorous solution with the intuitive solution. If these are the results, this is the note that P is going to be the probability of success, probability of the bad product. I think a very intuitive solution would be, how many of these we have? 8 observations. From that we have one observation here which is a bad product or which is success. We would probably say there is a success probability of 1 over p as an estimate of this p. Again, I say that whether this is a good estimate or not, but let's call it an intuitive estimate or intuitive estimator. Call it pi. Note that there is going to be a hat here. This is going to be an estimate of p, and please note that the distinction, not the distinction between estimator and estimate. This p hat pi is going to be an intuitive estimator for p, and 1 over 8 is going to be an intuitive estimate of p. We won't be knowing the p value because from sample to sample, due to sampling distribution of p hat, because from sample to sample we are going to have different observations in series, we are going to be obtaining different intuitive estimate values. Anyway, this is probably what you come up with. Let's see whether how maximum likelihood estimator falls with respect to that value that we may call intuitive estimator. If anybody can come up with other estimator, call it on your own and check with the maximum likelihood estimator. I hope we are going to find at the end. So what we are going to do is we assume that geometric distribution is valid. So the geometric distribution probability distribution for this whole sample is going to be equal to, and we are going to call it L, which is called likelihood, is going to be equal to 1 minus p to the power n minus 1 times p, where here p is the true value of the population parameter and n is the total number of observation here, sample size. But we don't know the p value. That is the question at hand. And you may say that this is already the probability density function. Why do we call it likelihood function? There's a reason for that, which I'm not going to go into. This is usually shown as probability of, let's say here, this is going to be n and also p. It is a certain representation. This is not exactly equal to probability, but I'm not going to go into that. But this is basically called likelihood function. So the procedure is pretty much simple. We would like to find the value of p which minimizes this likelihood function. But we do not usually just jump into the question and try to determine this minimum value. First, we find the logarithm of L. For most cases, this works very fine. So it's going to be equal to n minus 1 ln 1 minus p plus ln p. Note that you should be comfortable with how ln or logarithm works in multiplications. For those who have, if you have something like this, right, you can write it as log a plus log b to the power c, which is going to be log a plus c log b. Simple relations related with logarithm. Okay, now let's go to this part. So ln L is going to be equal to this representation, which unfortunately I messed up a little bit. So what we are going to do is we are going to find the maximum of this value. And in order to find the maximum of this value, we take the logarithm of L with respect, we take the partial derivative of logarithm of L with respect to all the distribution parameters. There is only the distribution parameter p here, so I'm going to take the derivative with respect to p. And when I do that and equate this to 0, instead of p, I'm going to be using maximum likelihood estimator, because this is the definition of maximum likelihood estimator. It is the value of p which maximizes this ln L function. And when you do that, n minus 1 is a constant here. 1 minus p, if you take the derivative, it's the derivative of here, 1 minus p is going to be equal to minus 1 here, divided by this whole expression. So it is, for those who can remember, ln u, this derivative with respect to, let's say, u, or u is going to be equal to, so let me say x here. It's going to be the derivative of x du over dx divided by this u value. So it's the u prime over u is the usual representation here, and it is what we do here. The derivative with respect to p, this whole expression is going to be -1 multiplied by n minus 1, and this whole expression here, which is u, right, 1 minus p, is written here. Okay, plus this is going to be equal to 1 over p is going to be equal to 0, but here we write maximum likelihood estimator. Please do not forget this. So when you put this to the other side, we are going to have n minus 1 here is going to be equal to 1 minus p maximum likelihood over p maximum likelihood. And this is going to be equal to 1 over p maximum likelihood minus 1. These 1 will cancel, and I'm going to have this expression. If I put 1 over p maximum likelihood here, is going to be equal to 1 over n here. And here is the very interesting thing. This is exactly equal to the intuitive estimate I have found. Here, n is actually equal to 8 number of observations. So the maximum likelihood also says this. If we have a number of n observations in a geometric series, just take the reciprocal of that n, you are going to find the maximum likelihood estimate of the distribution parameter of geometric random variable. So this is actually very much in accordance to our expectation or our intuition. Maximum likelihood estimator gives a very nice result. Now the second question, which is 7.35, Poisson process with parameter lambda, and we have a random sample size of n. Random sample size of n. Okay, first let's try to materialize this question. We are waiting for calls, let's say in a, this is supposed to be a telephone. Of course, it looks awful. Maybe I should have put a cellular phone. And I don't know how to, okay, this is a cellular phone. The old one, the very old one, Nokia. So these are the times when you have your cellular phone has ranked, and you would like to determine the in a random sample size of n your Poisson parameter here. Let's say that your phone, the number of phone calls you take is Poisson distributed, and you would like to determine the lambda parameter in your Poisson distribution. Let's take, for the sake of the question, t to be equal to 1. Therefore, lambda times t is going to be equal to lambda. So let's say this is 1 hour or 1 unit time interval. So what you do is this. The question, note that here the random sample size of n is going to be a little bit different compared to the other one. So we should materialize this random sample concept clearly. You wait for 1 hour and you record the number of calls you take. You call this, for instance, x1. 3 calls I have taken. And in the next hour, note that each 1 hour is independent from each other because it is derived from binomial distribution, Bernoulli distribution, where each event is independent from each other. In the next time interval, the second 1 hour period, you take 0 calls. In the third hour period, you take 4 calls. And you have all these for n time interval, and whatever the calls, number of calls you take. So this is going to be your sample, these values. We have n of these values of 1 hour intervals. And from these values, what we would like to determine is this parameter, which is going to be equal to calls per hour. So, but note that we need to put a head here. We don't know this value. This is what we would like to obtain. And here, to obtain this value, we are going to be using the maximum likelihood estimator. First, the intuitive solution. Given that you have these values, let's say that 0, 4, 1. We monitored our calls for only 4 hours for successive 1 hour period, and these are the values that we have obtained. 3 calls, 0 call, 4 call, 1 call. The question is, what would be your parameter estimate? First, the intuitive solution. The best way to understand the intuitions, just look at the units. Calls per hour. This is actually what we call a rate parameter that you should be familiar with. You are going to be taking a catalyst reaction kinetics course in the next semester, but from a couple of courses starting from high school, I think you are familiar with the chemical reaction concept. This is kind of very similar to what we call K in first order reactions, the which affects the reaction rate. So this is cols per hour, and for every hour we have these cols. And so I think, I don't know what your intuition says, but my intuitive answer, calling this with subscript, by the way, in statistics there is nothing like an intuitive answer with a subscript. I just made it out during this lecture. I kind of improvised. So it's going to be sum these values, add these values, 3 is 1, and divide by 4. And this seems pretty much seems nice to me. Without any theory or nothing like that, my intuitive answer would be here. I take 2 cols per hour. This is going to be my estimate of the distribution parameter for lambda. Let's see what does maximum likelihood estimator tells. So maximum likelihood estimator is going to be a joint probability density function of all, or it looks like the joint probability density function of all observations in the sample. So here actually previously I wrote it in this manner. Now this is going to be slightly different since I have each of them is a separate experiment. I'm going to be writing the probability density for each of them. Let's remember what the probability density for the Poisson distribution looks like. It's going to be exponential minus lambda. Note that I get rid of t taking to be equal to 1. It's going to be lambda to the power x, x factorial. So this is the number of calls in 1 hour. So L is going to be equal to the first one, those 3 calls would be exponential minus lambda, which I do not know, and lambda to the power x1, which is 3. But here I would like the general answer, so I'm going to leave it x1 factorial. This is the contribution of the, or let me put it that way, this is going to be the probability of x1 calls given theta parameter. Note that I have that additional theta put here just to remind you that this is slightly different. Although the computation is exactly the same as probability density function, the notation is slightly different. The details are not important. For the number of calls I take in 1 hour, which is observed as x1. Note that here x1 will be really known. It is going to be given to us. This whole thing is going to be given to us. From this, we are going to be estimating. Anyway, the second one is going to be lambda to the power x2 factorial. And it goes like this until exponential lambda lambda to the power xn factorial. Now let's make this look nicer. This is actually in a multiplication sign using a product. I to from 1 to n exponential to the power lambda to the power xi factorial. Okay, can we look nicer? I think we can. This is going to be actually equal to, note that we don't have any what do I say, indexed I here. So you can take this as you can easily see from this product, this is going to be equal to exponential lambda multiplied by n times, which means exponential minus n times lambda. Probably I try to explain it awfully, but I think you understand mathematics. And this whole thing is going to be, this product can be written as lambda to the power summation of xi, because all these x1, x2 are, when they are raised to the power, lambda is raised to the power to those values, they are going to be sum over, and this is going to be divided by xi factorial, but with a product. This is very easy mathematics, but I somehow messed it up trying to explain it. Anyway, this is L. Now what I'm going to do is I'm going to take the logarithm of both sides to make life simpler. So this part is going to be equal to n lambda, because ln, let's remember, this is going to be, if you have something like this, you have, this is going to be equal to a, because logarithm of n, natural logarithm of e is equal to 1. So we have minus 1 and lambda here. plus then this is going to be again come before the ln term, ln lambda. And this seems confusing, but hopefully there's going to be a very easy trick. Let's keep it as it is. Note that, well, there's going to be, since this is in the reciprocal, is going to be a minus sign here. So let me get rid of that. Now we are going to take the partial derivative. If you think this gets confusing, or complicated, it's not going to be actually. Believe me, usually we have very simple solutions. Since this is the only parameter here, note that n is not the parameter, right? Because the number of experiments are known. All xi values are known here, right? And we know the number of experiments. So at the maximum likelihood estimator, this is the parameter of interest, the derivative is going to be equal to 0. So the derivative of the first term is going to be very easily this one, plus the second term is going to be equal to, this is 1 over maximum likelihood. And this confusing term, one may think that how can I get deal with this term? Note that these are all related with each of these sample values I have observed. They are not functions of lambda value. They are already known, so there's going to be no contribution here. The derivative is totally equal to 0. So this is going to be equal to 0. Now the rest is very simple. You put n to one side and you just change the location of this one and this term here. Therefore, maximum likelihood is going to be, estimate is going to be equal to over n from I1 to n. And this is basically simply x bar. And the very interesting solution. This is exactly equal to the intuitive result, which is sum all these values and divide by 4. We have obtained the maximum likelihood estimator, which is found by Fisher, one of the greatest achievement of statistics, I may say, gives you the intuitive solution. Of course, it's not always going to be the case, but I just try to solve these questions to warm you up to this topic, I may say. Okay, and the last question is, let's see. We have a certain probability density function. I'm sorry, I'm writing the wrong probability density function. Okay, we have this probability density function here. Note that this may be a linear one, or if theta is some value other than 1, it's going to be a nonlinear, a curvature, something like this, whatever. So based on a given random sample of how many elements? N. All right, and determine. So we are going to be here, this is going to be, we don't know anything about this distribution. Let's say these are the, since it's between 0 and 1, this may easily correspond to some, let's say, mole fraction of a component. You randomly take samples and you determine the mole fraction of that component in that mixture. And you somehow know that it is distributed, its distribution shown with that representation. But you do not know this parameter theta. Okay, so as I said, try to say when theta is equal to, for instance, 1, this is going to be equal to x raised to power 1 is going to be 3x, I guess. Yeah, but actually this cannot be. Well, actually, I just realized that we may do a trick related with this. Well, here is the trick. Actually, since this is going to be equal to 1, this should be equal to 1, between 0 and 1. Can't we find, using some mathematical, I cannot even say a trick, and we would like to find this parameter here. Okay, that's a note that this just again I'm improvising. So this is going to be x raised to the power, oh, this is difficult. So when it's 2, what do? We increase it by 1 and we divide it. Yeah, it's going to be like this, 0 and 1. So this is going to be 1 over 2 theta 1. This is going to be like that. I don't think I need to put this here. Let this be 2 theta plus 1. And now this is problematic because this is not always going to be the case, right? If this is, for instance, minus 1, then this is going to be an element. But just let's work it out, right? Assuming that this is not minus 1, I think this is going to be valid. So when we put 1 here, 1 raised to the power whatever value here is going to be always 1. So therefore, this is going to be equal to interesting. If I'm not wrong, we can exactly find a solution here. 2 theta 1 is going to be equal to theta plus 1. So theta is going to be equal to 0. Okay, so therefore this is going to be 0. So this is going to be uniform distribution. Yeah, that's one answer. So one answer here would be between 0 and 1, you are going to have this distribution here. Now the question may be, can there be any other value of theta which is going to satisfy this system? For instance, if this is minus 1, we may say, right, then this integral is going to be x raised, is going to be minus 1 dx. So this is going to be ln x from 0 to 1, but 0 is going to be problematic here. So I guess this is the only solution. I think there is a problem with that question, right? Because the only solution, as far as I can see, seems to be this solution, for which you don't need to use maximum likelihood estimator or anything like that, and it can be determined just by using the fundamental the fundamental idea behind probability density function. But for any case, let's try to solve this question and let's see using maximum likelihood estimator, and let's see where is it going to go to. Maybe we are going to obtain the very same solution, which I pretty much doubt, because maximum likelihood does not use any information related with that constraint related with probability density. Anyway, so we have different x values, let's say from 0 to 1, and we would like to determine this theta value. So here for this case, the maximum likelihood estimator is going to be equal to all these values, x1 theta, x2 theta, probability xn theta. And here they are going to be equal to 2 theta 1 plus x to the power theta x1 times 2 theta plus x2 theta. It goes like this, 2 theta 1 xn theta. As you can see, this is very much similar to Poisson distribution approach. So it's going to be 2 theta plus 1 raised to the power n. And then these are going to be x1, x2, xn. So it's going to be x1, x2, xn. So let me write it that way. Product of xi raised to the power theta. I'm usually confused about this whole thing. Now, 2 raised to the power 7 and 3 raised to the power 6. 7 is going to be equal to 6 raised to the power 7. Well, it's just me actually, probably. It's probably very simple stuff, but when you have the same orders here, you can do this thing, and the idea is you have all these 2 7 times and 3 7 times. Therefore, when you multiply those, you are going to 6 7 times. Probably most, or maybe all of you know, see this as a very simple thing, but that's usually what I'm confused of. Anyway, 2 theta plus 1 raised to the power n, and the product of xi values here raised to the power n. Okay, this is going to be our L. Then when we take the natural logarithm, it's going to be n times ln 2 theta 1 plus this thing here, ln xi, product of xi. That's great. Then we take the partial derivative and make it equal to 0. Let's see, we have n here and we have 2 here, so it's going to be 2. Where's my cursor? And 2 theta maximum likelihood plus 1 seems okay, and this one is going to be ln pi xi. All right. Then what we do here is we put this to the other side and this one to the other side. So 2 maximum likelihood plus 1 is going to be equal to 2n ln. Note that, let's make this look nicer. It's going to be ln x1, x2, xn. Therefore, this is going to be equal to ln x1, ln x2, blah, blah, ln xn. Therefore, this is going to be summation of ln xi. All right, this is better. This one inside this product doesn't look nice. So it's going to be ln xi, I from 1 to n, and somewhere here, yeah, there should be a minus sign. So let's try to finish this. This is going to be equal to 1 over 2, and this will cancel. So when I put this to the other side, it's going to be minus 1 minus n ln xi. Well, this is the maximum likelihood solution, which doesn't look like anything that I know of. Maybe, okay, I can put it that way. Minus 1 minus 1 ln xi from 1 to n divided by n. Now that's maybe, I can also put this minus sign here and plus here. As you can see, I kind of do very simple mathematics, but try to make it look nicer. And I can put this here minus as a 1 over xi here. So when I do that, what I obtain will be something like this: 1 over from I1 to n ln 1 over xi divided by n. So basically minus 1. So basically this is going to be 1 over 2, I'm sorry. This part is going to be the average of 1 over x ln xi values. You take the 1 over x, you take the ln of them, and you take the average. So I can show it that way. So maximum likelihood, now this is actually a complicated solution, something that I wouldn't ask in an exam, so believe me, this is what I can say here, what I can guarantee here. So as a kind of this bar here shows the average minus 1 over 2. So take the reciprocal of x values. So x values would be equal to, let's say, 0.2, 0.6, 0.8. These are the concentration values. Take the ln or reciprocal of those, and then take the ln of those, and 1 over, if I haven't done any mistake, this seems to be the answer, which I pretty much don't like, actually. Indeed, I even doubt whether this is going to be whether it is going to give a positive. The result is not going to be positive, it's going to be negative, because as you can see, when you have 0.2 here or anything smaller than 1, this value is going to be greater than 1. So this value is going to be can I guarantee this to be greater than 1.2? I doubt so. Anyway, well, this turns into a more like a numerical mathematical exercise, which I don't want to go into. But if I've done everything correctly, this seems to be the maximum likelihood estimator. But as you can see, I didn't like this question. Probably there may be a mistake even with this question, because there is the problem that this probability density function is not, seems to be at least, not very well defined. Anyway, so that's all I'm going to talk about, the maximum likelihood estimators. I hope the idea is clear. There's an example in your textbook related to normal distribution, especially. Well, since the normal distribution seems a little bit more complicated function, the whole thing seems complicated. That's why I skipped that. But for those who are interested, you may try that. There is also the very tricky example. What if you have a uniform distribution? How to determine its parameters? It doesn't obey to this form. Take the ln and take the derivative with respect to the 0. That's all. Also, I have skipped this part. But as I said, that's all I'm going to talk about. Maximum likelihood estimators. But if you are going to continue to be a data scientist or something like that, this is going to be a pretty much important topic. Okay, that's all.